Today we're going to continue the conversation about converging and diverging series, and we're going to build on the fact that yesterday we found that if we had a limit in the ratio test of 1, that really didn't tell us anything about the series, whether it converged or diverged. So if we end up with a ratio test of 1, then we're going to move on to this thing we call a comparison test. Now, there are two comparisons we're going to make. We're going to make a comparison to a convergent series and to a divergent series. Remember, if we compare to a convergent series, we know that every term in a convergent series is going to move to a sum that has a limit. And every term in a divergent series is going to move to a sum that goes to infinity. So if we can show that each term in a convergent series, talking about this up here, each term in a convergent series is actually greater than a term we're comparing it to, we can say that that new series is convergent. Let me give you an example. If I say, here's the value of a half, a fourth, eighth, a 16th, etc., etc., etc. And this is convergent. I could find that out. And I want to compare the series in blue against that. And let's say the series in blue is a 10th, a 20th, a 40th. This is fairly obvious, but I'm giving you the example anyways. And let's say I didn't know anything about this series. Since I know each of these terms moves to a limit of a known value, let's say 0 in this case, which it will be, and I can show that each of these terms is less than the term in red, then I know since this converges, the red series, the blue must also converge because it's actually less than the red. Likewise, let's talk about the second piece now. If I were to say 2, 4, 8, 16, etc., etc., we know this would diverge. And let's say, for instance, I didn't know what this series would do, even though it's going to be relatively obvious what it does. 4, 9, 16, 25, etc., etc. And I knew that the terms in blue diverged, and we could say that each term in black is greater than each term in blue, then the series in black must also diverge. That's what these two say. I'm going to show you the two series we're going to commonly compare to. The divergent series we're going to compare to is 1 over n. The convergent series is 1 over n raised to the p, where p is always going to be greater than 1. And note down here that all terms in these series that we're making comparisons to must be positive. So we can't have an alternating series like we have in some situations. So this is only going to work for specific cases. Now you might think it odd that this actually diverges because the series actually has a limit. It goes to 1 over infinity, which goes to 0. But if you take and group these in a specific way, these two end up equaling a number that is greater than a half. If I go from 1/5 all the way out to, let's say, 1/8, and I group all those terms, those numbers are greater than a half, etc., etc., etc. So as I group more and more terms like that, I'm finding that I'm adding a half over and over again. And that's like an arithmetic series, and we know arithmetic series diverge. So that's why 1 over n diverges. If I did the same thing here, this would be like a quarter, a ninth, a 16th, forever and ever and ever. These numbers don't grow like these numbers, and it actually converges. So those are the two series we're going to make comparisons to. Let's start with an example. I'm going to take and compare each element in black to either a known convergent or divergent series. Let's do it. This divergent series of 1, a half, a third, a fourth, a fifth, etc., etc., etc. I'm going to compare the black against the green. And the first term really doesn't matter, as it said in the previous explanation. So if I compare 1 over root 2 to a half, it's actually going to be bigger. 1 over root 3 is bigger than a third. 1 over root 4 is bigger than a fourth. 1 over root 5 is bigger than a fifth. Since every term in black is bigger than every term in green, and the green is divergent, I can say this diverges as well. In the next example, it might help if we take and rewrite this. So this is a half, this is a sixth, this is a 12th, this is a 20th, etc., etc., etc. And I'm going to compare that against, let's go green again. So I'll compare it against 1, a half, a third, a fourth, on down the line. Well, I know that a half is less than 1. I know that a sixth is less than 2, or a sixth is less than a half. 12th is less than a third. 20th is less than a fourth. Now, I know this green guy diverges. In order to show that the black diverges, I have to show that each term is greater than the green terms. If it's less, I just know that it's less than something that goes to infinity. How much less, I don't know. So this comparison really did me no good. So what I'm going to do is I'm going to take and make another comparison with a known convergent. And we'll let p equal 2 in this case. So I'm going to compare it against these blue terms of 1, a quarter, a ninth, and a 16th, and on down the line. So a half is actually less than 1, the sixth is less than a quarter, the 12th is less than a ninth, a 20th is less than a 16th, and this will continue to happen over and over again. So since every term in black is less than every term in a convergent series, we can say that this series converges. Last, I have a series here, and you can see right away you pretty much know what the answer is, but we're going to do the comparison anyways. And I can say I know what the answer is because after we pass 6/8, I get numbers that are greater than 1, and I'm adding those over and over again. It's just that this a sub n value in the ratio test would give us something we don't know enough about. So we'd have to use the comparison test to go through it. So let's go and compare this to 1, a half, a third, a fourth, a fifth, on down the line. So we know that 1's actually greater than a half. We know that these two are equal. 6/8 is greater than a third. 24 over 16 greater than a fourth. Greater than a fifth. And here again we're adding greater than 1 on down the line. Now even though this first term is less, the first term doesn't matter. The second term is equal to, all right, but then everything thereafter is greater than this divergent series. And since this is like adding halves over and over again, this is bigger than adding halves over and over again. So therefore, this is a divergent series. Do some comparisons with these two. Now, notice the questions I gave you are in sigma notation, which means you have the equation of the series. It will be helpful when you take and make your comparisons to expand that series out. So plug the numbers in, get about 5 terms, make those comparisons, and then come up whether it's convergent or divergent.